Today we are going to talk about the benefits of using concentrated photovoltaic energy compared with existing PV panels. PV panels are systems that utilize semiconductors to convert solar energy into usable electricity. The IEA estimates that the move to a sustainable, carbon-free energy system requires solar power's share of the electricity mix to reach 15% by 2050, necessitating a more than four-fold increase in electricity generated from PV over the next 25 years. Unfortunately, it is doubtful that current PV technology alone can drive this growth. While solar energy is completely renewable, it is not available at all times or completely reliable because sunlight varies with location, thus reducing the capacity factor. Furthermore, the most common panels are crystalline silicon, which make up 90% of the PV market. Contemporary crystalline silicon cells are only about 16% efficient, and gains in efficiency have been slowing. Together, these challenges can cast doubt over PV's ability to continue to grow as a renewable energy source for electricity. Moreover, because of PV's low efficiency, the need for mining of rare earth metals, and the intensive and sterile manufacturing process, the embodied energy of the panels themselves is high. This takes away from the net energy savings that are incurred from using renewables instead of fossil or other fuels, and increases costs. An emerging kind of PV called concentrated PV, or CPV, could drastically reduce these problems. As its name suggests, concentrated PV panels capture the maximum amount of available sunlight by concentrating it through the use of multi-axis trackers and special lenses. Though CPV currently makes up less than 1% of the PV market, the continued development of CPV technology in the near future will likely yield dramatic increases in global production and use. CPV is growing for three main reasons: increased efficiency, cost effectiveness, and decreased embodied energy. But how specifically does CPV accomplish these improvements? It starts with lenses, which allow CPV to concentrate sunlight. One possible mechanism is to use a Fresnel lens, which directs sunlight on the panels with a jagged sawtooth pattern, and then directs all the light to a single point using concentric circles. A second mechanism is prismatic covers. These can be inserted onto solar panels and are made with plastic, which are inexpensive and easily replaceable. The plastic covers direct sunlight into the cells and help negate the problem of shadowing from nearby cells. Using lenses to gather more sunlight per cell makes incorporating more expensive but higher quality cells economically feasible. These cells may include black contact cells, which put the positive and negative components of the semiconductor onto the back of each cell while also reducing shadowing effects, or multi-junction cells, which contain different semiconducting components. These cells can make use of a broader range of the sun's wavelengths to generate electricity, and are therefore far more efficient than the cells currently used in PV panels. You can see the effects of concentrating solar versus not. This is the energy produced for fixed plane panels, tracking panels, and CPV at one site in Arizona for the same investment price. Equally as important, because of CPV's system's higher efficiency, the manufacturing of CPV involves much less embodied energy than is involved in regular PV production. Some researchers have found that it only takes 0.9 years of electricity production for CPV panels to recover their manufacturing energy, compared to 1.8 years for a crystalline silicon system. The lower energy associated with production means that CPV also has a lower greenhouse gas footprint. It is estimated that CPV manufacturing is responsible for 27 grams of CO2 per kilowatt hour, compared to 39 grams for a crystalline silicon system. These energy and greenhouse gas improvements over current models will only increase as CPV technology continues to develop. While concentrated PV installations are cost-effective and becoming globally adopted, there are some issues with CPV. One concern is that, unlike regular PV panels, CPV panels can only make use of direct sunlight. A region like New England that lacks this may have large amounts of sunlight available for regular PV, but a comparably small amount for CPV. A second issue is that concentrating solar makes the solar modules very hot, which can decrease efficiency and increase wear. One experimental technology utilizes incident energy that is wasted as heat by combining PV technology with thermal concentrator technology. The incident heat can then be used to heat water. Concentrated cell technology can also have unintended environmental consequences, like increased mining of rare metals like germanium. Since the technology is prototypic and may continue to be innovated, there is uncertainty regarding CPV's total environmental footprint in years to come. Due to these and other issues, it is important to remember that solar energy, even when concentrated, should be part of a movement toward better energy usage and is not a panacea. However, the future for concentrated PV definitely looks bright.